All right. So our next discussion, following our discussion of instantaneous acceleration and instantaneous velocity, is a description of the kinematics equations. Right? I had introduced them before. Kinematics equations. I introduced kinematics as the mathematical description of an object's state of motion at any given point. So now that we know how to describe the average velocity and acceleration of an object on a particular trajectory, as well as the instantaneous positions, velocities, and accelerations of an object at any given time, now we can look into the kinematics equations, which are very general descriptions of the present position, velocity, and acceleration of an object at any given time. I sort of gave you an introduction into how these things work, like the position and the velocity and the acceleration, but now I won't derive, but I'll tell you and I'll show you the very general equations for position, velocity, and acceleration. So if we look in the x direction, just to simplify our discussion, we start in the x direction. The most general equation for an object moving in the x direction is a combination of its initial position. This is what's the position right at the start when we started looking at this thing. Oftentimes this will be considered to be 0 because we kind of want to think that we start looking at something at the 0 point, but sometimes we might not consider the point that it currently started as a 0 point. We might look at it with reference to some other point that's 0, that we consider to be 0. So this is the initial position in the x direction, plus the initial velocity in the x direction, times time, the time that the object is moving, or the particular time that we're looking at. And this is the initial velocity in the x direction, so the velocity that the object is moving in the x direction when we start looking at it, plus 1/2 of a times t squared. A being acceleration, t being time. And acceleration, as we said, is constant in these cases. This is a sort of look at objects moving in a trajectory that's called uniformly accelerated motion. So in some cases, in more advanced cases, acceleration might not be constant or might not be assumed to be constant. But for pretty much all of our discussion throughout this course, I will assume acceleration to be constant, to be a constant value. So we can also have a description in the y direction, position in the y direction with respect to time, which is the initial y position, plus the initial velocity in the y direction times time, plus, or I should say minus, and I'll tell you why, minus 1/2 of gt squared. Now, this is the gravitational acceleration, the rate of gravitational acceleration on Earth. It's a negative value because gravity acts down on objects. This y position is a position in the vertical component of an object's trajectory. So, in this case, we have this being equal to negative 9.81 meters per second squared. Negative 9.81 meters per second squared is the acceleration of gravity on Earth. And in this discussion, this is the most general form of the position of an object at any particular time that's in motion in the x direction. And this is the very same thing in the y direction. at any particular time. Now, these two things are separate components of one total position, what we would call like the position vector. When we get into vectors, I'll sort of talk about that more. But these are kind of like how when you learned about Cartesian coordinates, you learned that any point on a Cartesian graph has to be defined by its x and its y. Well, in this case, any position of anything on Earth or anything that we're looking at a certain reference frame, in a Cartesian reference frame, will have to be looked at in terms of its x and y positions. And these operate separately of each other. The x position has nothing to do with the y position. The initial velocity in the x direction bears no influence on anything that happens with the motion in the y direction. And nothing that happens with the x direction affects any of the motion that happens in the y direction. So with these formulas, now we can derive a more general equation for instantaneous velocity. These were both formulas for position. Maybe we can even say instantaneous position. Now we want to look at instantaneous velocity, and we'll just use this one. You know what? I'll actually use this one too, though, because it's important to discuss the differences here. If we wanted to find the velocity in the x direction, the instantaneous velocity at any particular point in the x direction, we take our position function, and like I described in the last video, we take the derivative. And that derivative, in this case, this is a constant, so that becomes 0. Here, in this case, when we do the derivative, the t goes away, and we have the v initial of x. And here, the 2 cancels out the 1/2. So then we have v initial plus at, acceleration times time. And this is v of t in the x direction. In the y direction, you would have dy of t, dy dt. And that equals to, once again, this goes away, so that's 0, plus v initial in the y direction, because once again the t goes away, minus gt. This is the velocity in the y direction. Okay, and with these definitions, it's clearly, in both of them, it's clear to see that there's a initial position, initial velocity, and a final velocity. And that'll be important. Like, we know the initial velocity when we started looking at this object, and then with this formula, once we know the acceleration and we know what time we're trying to look at this thing at, we can find the final velocity at that particular point in time. So it is of value to describe the fact that time, the formula for time, is equal to, in these two cases, I'll just use a formula in this case, but it's basically kind of the same thing here, is equal to v minus v initial over a. Right? That is the formula for time in the x direction. This is if we were saying vx. In this case, we would have v of y minus v divided by negative g. So these are very similar formulas. The only difference really is the fact that the velocity in the y direction and the velocity in the x direction are different things. I should also point out that these are not the same. These initial positions are not the same. This is v initial in the x direction. This is v initial in the y direction. And the accelerations are different. So, but really this is a general equation. You can switch out the x's for the y's if you want to talk about the velocities in the y direction, and you can switch out this acceleration with negative g. You basically have the same underlying structure. And now I want to use this equation, this general form, because it's important to deriving another kinematics equation that we can use. So really, before I move on, let me just quickly state that two of the very important, or more actually, what do we have, four of the very important kinematics equations to know, just right now, just from what I've already discussed them, are these two, this, which is basically this. You can kind of think of them as one equation. You can even think of these two as one equation. They only change based on what direction you're looking at, but the overall overarching structure of them is the same. So really, it's two kinematics equations. It's this and this, and also this, actually. So I guess three. So we would have three equations here. This particular thing, what I'll do with this general format for the formula of time is I will substitute it back into this equation here, and we'll get another equation that helps us. Because really, in these kinematics equations, what we want to have is a nice sort of tool belt of equations to use, so that way, we can always analyze the motion of an object, because sometimes we might not be given every piece of information that we would like. We might be missing some piece of information, but the more kinematics equations that we have, the more equations we have that don't require maybe every detail of the object's motion. So using what I've established so far, I will now clear some space over here. Clear some space. I will clear this space, and I will now use that equation that I wrote down before, which was V minus V initial divided by A. That's the general equation. And I will plug that back to everywhere where there's a T in the equation, in this equation here, plus V initial x direction times t plus 1/2 of at squared. Everywhere where there's a t, I guess in this case I'll just specify that it's the x, but really this equation, the equation that I'm going to be working towards, will work in the y direction as well. So just think of it as a general structure here. So if I plug this t in to here and here, what will happen is I will get an equation that looks like this. Continue over here. A we will get this, and I'm not going to do the algebra out for you because I'm pretty sure you can do it if you're sort of taking this course. But what you'll find out is when you break down all this algebra, you will get a final thing that looks like this, that the v in the x direction squared minus v initial in the x direction squared is equal to 2a times x of t minus x initial. This squared minus vx squared, which is the final position in the x direction, minus the initial, the final velocity in the x direction squared, minus the initial velocity in the x direction squared, is equal to 2 times the acceleration times the difference between the final point and the starting point. And this is something that we call displacement. And let me discuss what displacement is. So displacement basically means the straight line distance between the point where you end up and the point where you started. So if I have a point, if I start at this point and I end up at this point, call that x of t, right? And I take this convoluted path, the total distance in miles that, or whatever units that I'm using to get here that I used is the distance. That would be the whole entire, every sort of curve and in this convoluted path here, the distance along all of this. However, the displacement is just a straight line distance from here to here. This stuff here, this crazy stuff, would be the distance. That is, if I took that path, I could have taken another path. Whatever path I take, the distance will be the actual amount of ground that I cover to get to that path. But the displacement is just simply the difference between the straight line difference between where I ended up and where I started. And that's what this is here, because this doesn't take into account if you took some sort of crazy convoluted path or whatever. It basically says, I'm just basically looking at the straight line distance between where I ended and where I started.